This is the continuation of lecture 17. I apologize. Something happened with the last video. It ended abruptly, but I checked it and everything should have been good for that last instant center problem we did with the garage door. So I want to go ahead and do the juggling pin, which looks like this. And so the entire pin is 20 inches long. So 12 inches here, 8 inches at the other end. So notice our unit's 4 feet per second. So we know that this distance is going to be 1, and this distance is going to be 8/12. So, or 3 or 2/3. And so we know it's rotating at 30 radians per second about G, and it's moving upward also at 4 feet per second. So we want to find out what is the velocity of A, what is the velocity of B, and where is the instant center at this point, since the thing's translating vertically as it's rotating about its center of gravity, which is pretty much what we're going to see throughout the chapters. We'll do a little bit about later about rotation about non-center, but for the most part, we're going to assume that things are rotating about the center of gravity as they're free. Okay. So here's what the object looks like. Not quite as colorful, but I guess I could put a little eye there. It looks like some weird fish. But so we have the 4 feet per second going up from G. We have A, we have B. So we want to know velocity A, velocity B. So we can see that if by intuition, if it's rotating counterclockwise, velocity of V is going to be going that way. And it's safe to say velocity of A is going down. All right. So we want VA. Well, we know VG, right? It's 4 feet per second. So we'll say velocity of A equals velocity of G plus velocity of A relative to G. Or we can write it as velocity of A equals, we know velocity of G is 4 in the J direction, plus omega AB crossed with RA relative to G. And again, everything as vectors. So if we write RA relative to G, sorry, make sure my vectors are consistent. I know it's going to be -1 in the I direction because it's a foot. So going from G to A is -1 foot. And then I know we'll probably need RB relative to G later, and that's going to be going from there to there is going to be 2/3 I. All right, so there's that. So if we go ahead and substitute in, we know VA again is 4J, and then that's going to be plus 30K crossed with minus I, essentially. And so we get 4J minus 30J, which gives us -26J feet per second, which makes sense. We predicted it'd be going down, and that's what it did. All right. Then we can do the same thing. VB, that's going to equal VG plus VB relative to G. So VB is going to equal 4J, and then that's going to be plus 30K crossed with 0.667 I. And so this turns out to be 20J. So 4J plus 20J, we get VB equals 24J. All right, so that's going in that direction, which makes sense. So now the instant center. So instant center, we need to figure out where it's going to be. So we're going to go ahead and look at it in terms of here's our diagram. Actually, let's use a different piece of paper. So what we can do is we can redraw this, or we know it's that and that. And again, this is the pin. I just haven't put the bulk in it, or just did. So here we have G going like that, and then we'll say that that's our point C. So there's C, and there's G right there. So velocity of C equals velocity of G plus the velocity of C relative to G, doesn't it? So just like we did the same thing as before, we know that we can write this relationship too. So you can kind of see where this is going because we know at the instant center, this is 0. So we're going to say 0 equals 4J, and then that's going to be plus 30K. That doesn't change. And then that's going to be crossed with XI because really we're looking for this distance X. So if we do that, we get this equals 4J plus 30XI. All right, and so if we solve, it's basically X equals negative 4 over 30, which equals, that's 4 over 30 feet, sorry. Yeah, negative 4 over 30 feet, or negative 1.2 inches. All right. So that's how we did that. So remember, Vincent center's velocity is 0. We have velocity G, C relative to G. The only unknown was our distance. And there we have it. Okay, so I think velocity and instant center, hope that's makes you understand. We'll probably end up doing a few more examples of that at some point as we go through acceleration. So I want to talk a little bit about acceleration now. We will definitely revisit it and go through an example. I don't think I'm going to do an example in acceleration online because I want to be able to pause and show you different places, and it's better to do that live. So let's just review acceleration though. So here is the drawing that you see in the book. Now, what is it exactly it means? So treat velocity and acceleration as two separate entities. I mean, we need to know the tangential velocity, of course, to find the acceleration in the normal direction, but we don't have to solve them. We can solve them separately. So imagine that you're given the velocities you need, and now you're just looking at acceleration. So the big difference you notice is that instead of just having a velocity of b relative to a in this picture, you have an acceleration b relative to a, but you have it in two dimensions, normal and tangential. And so what that equates to is when we when we write out what we're looking at, if we were to say, for example, write AB equals acceleration A plus the acceleration of B relative to A, then we know that this could be, in this case, this could be broken down into acceleration tangential plus acceleration normal. But most of the time, and how would we get that? We know that that's going to come from the, most of the time that's just going to be given as something in a single direction. So backing up, let me say that this, most of the time, for a single point, you're just going to be given something as a value in ij components. But when we look at this one, the AB relative to A, because of the nature of the perpendicular vectors, so remember that we say that we have this plus that, and then that goes to that. So really what we're saying is that that's my acceleration of A, and that's my acceleration of B, and then I have to add that to it. So that's my acceleration of B relative to A. But of course, we know that we break that into its 90-degree components of acceleration of B relative to A tangential, acceleration of B relative to A normal. You don't see that on this. So This will usually be given to you just as that, same with this. This one here, though, if we bring it down, that's where we're going to have our alpha in the K crossed with R, B relative to A. And then this is going to be, and that's our acceleration in tangential direction, and then minus omega squared R, B relative to A, where that's our angular velocity and then distributed through the vector. Okay. So that's the application of it. It actually, that's all there is really. It looks more complicated, but it's always going to look this way, no matter how, at least in our class of our special situations, that's what you're going to see. So I would like to do one example of acceleration, and this is an easier one. It follows a similar pattern. It may look familiar. We did this with velocity, but it follows a similar pattern to finding velocity. And the sense is that we're going to use the omega of dE that we're given. We're only given that the omega of dE is 20 radians per second here. And we want to find the omega of dB and AB. So we'll use velocity and we'll use velocity first, but then we'll apply that to our acceleration. And you'll see that the process is fairly similar. And so this will help get you ready for the more complicated problems that we'll do next Monday when we meet. Okay, so let's go ahead and look at it. Here's what I've drawn. So I would take a moment, pause, and draw what you think you need to see as far as the sketch. So it's a little out of proportion. 24 inches is the full width, 6 inches is this bar DE, 10 inches is the height, and then there's another 8 inches up here to that. All right, and so we want to find AB, we want to find BD. We know DE is 20 radians per second clockwise. So we can write that as negative 20K. So omega DE is negative 20K. So first thing, if we look at our bar here, if that's E and that's pointing up, well, we know that officially you could write it as VD equals VE plus VD relative to E, right? And you know that VD relative to E has to be perpendicular. But because VE is a fixed point, we know that that's 0. So we know that the velocity of D and the velocity of D relative to E are the same. And that we can conclude is just going to be equal to 20 radians per second times the distance, right? So D relative to E means we go D relative to E means we go from E to D. So we know that it's going to be 120 inches per second. And so it would be a negative, right? It would give us a negative going in this, or it's going up, but so we know that it's going, velocity is clockwise. So anyway, so we know the direction. That's the important thing. We know it's 120 inches per second going up, or we just take 20 times 6. So omega times R equals V, or 20 times 6 gives us 120. So now we have that. All right. So now, like before, we're going to create a velocity for each end. And because we need to we need to know the velocity each end, similar to what we did before we get an acceleration. So we know that the velocity B equals velocity of D plus omega BD crossed with R, B relative to D. And so if we do that, we end up with VB equals 120J plus omega BD crossed with 24I plus 10J. So this should look familiar, and I'm just going to introduce this part and then give you the answer since we already did it before. So that gives us 120J plus 24 omega BD J minus 10 omega BD, and that's in the I. All right. And then we do the same thing for, so this was for rod DB. We do the same thing for rod AB. So for rod AB, what's that going to look like? Well, we know that the velocity of B at that side is going to be equal to omega AB crossed with RB relative to A. Sorry. B relative to A. So we end up with the same thing, omega AB. And the reason we know this is because we know that the velocity of B, we know that would normally say equal the velocity of A plus velocity of B relative to A, but we know VA is 0, right? Because it's a fixed point up here. That's where I got that from. So that's fixed. So that's why we just immediately jump to the cross product, which is always going to be how we represent that. So we have omega AB in the K, and then that's going to be crossed with minus 8J. So that gives me an 8 omega AB in the I. So again, we're going to do the same thing. We have this equation here. We have VB equals this equation here. Equate I and J like before. Negative 10 omega BD plus 8 omega AB. And if you already remember this, you can fast forward until I get to the acceleration. But unfortunately, if with these problems is you have to start with velocity first because you need that value in order to do acceleration. And then our J is going to be 120 plus 24 omega BD. And then that'll equal 0. So we solve them, we get what? We get negative 5 radians per second, and we get 6.25. So remember that. That's from last time. All right, so now we want to look at acceleration because that's what we needed. Or that's what we're looking for. So I'm going to go ahead and let's write note omega BD is equal to negative 5 radians per second, and omega AB is 6.25 radians per second. All right, and that's their values relative to the clockwise or counterclockwise. So, all right, so now what's next? So now we're going to go and look at, again, rod DE here. And what is our acceleration? So, well, we're told that it has a constant omega. So that means that if it's a constant omega, omega equals a constant. Therefore, our acceleration tangential is 0. So the acceleration of D is going to equal just omega dE squared times RD relative to E. All right, so you ask, where's the negative? Well, again, remember that this is just to give us a this is a scalar. This isn't a vector we're doing here. All right, we're just multiplying this by this. And so what we're saying is that we have 20 squared times 6 inches. And so we know that the acceleration is 2,400 inches per second squared. Now, again, scalar meaning that from looking at dE, I know that if it's accelerate or velocity is going that way, I know its acceleration is going that way. So I could have done a negative here, and then I could have done d relative to e, right? And it would have been e to d. So if I go e to d, I would have gone a -6. So if I had done it the -20 squared and then distributed by a -6, I still would have got 2400. So that's why you don't have to worry. That's why I'm saying the negative sign is when you're dealing with vectors, you want to make sure you include it. But if you, from a scalar viewpoint, if you know what way it's going, then just 20 squared times 6, you have the magnitude of the value. That's what we wanted. Okay, so now we want to look at the rod BD. So for that, we know that we're going to write acceleration of B equals acceleration of D. And then that's going to be, we know plus B relative to D. So I'll write this again, B relative to D, which we know is going to be acceleration of D. And then that's going to be plus alpha BD crossed with R B relative to D. And then minus omega squared BD times RB relative to D. Okay. So, and then we'll go ahead and put in our other values. So we have, if we were to write this out, what would this equal? It'd equal 2400 I, and it's positive because it's going to the right. That's my AD, right? Again, all vectors. And then we have plus alpha BD in the K direction, and that's crossed with what? 24I plus 10J. And then that's going to be minus, and then omega BD we know is 5. So minus a -5 squared. And then that's going to be times 24I plus 10J. All right. So that's my one side. That's my AB. And you can maybe see where we're going with this, because we're going to say this is AB, but then we're going to go to the other side. We're going to go to rod AB, right? So we did rod BD. So we started on this side. We got our acceleration relative to B using this and this end, right? AD. So now we're going to go to the other end. So we're going to say now that the acceleration of B going from the other end equals what? Equals the acceleration of A, which is 0. And then that's going to be plus alpha AB crossed with R B relative to A. And then minus omega AB squared times RB relative to A. Okay. So just like before, we'll put in what we know. So AB equals, and then that's going to be our alpha AB K. This is K, of course, crossed with, and then what is it? It's a -8J. And then minus, and we know that it's going to be 6.25 squared, and then that's going to be 8J. All right. So now what we're going to do is we're going to take, we'll call this equation 1, equation 2, and we're going to set them equal, right? Because we have AB here and we have AB there. So we set these two pieces equal. Notice then we'll have alpha BD and alpha AB. And that's all that we won't know. And so you can kind of see where this is going. We're going to set them equal, and then we're going to separate their I's and their J's, and then we'll solve. All right. So if we do that, we end up with something that looks like 2400I plus 24 alpha BD in the J minus 10 alpha BD in the I minus 600I minus 250J equals 8 alpha AB I. So this is a AB, so 8 alpha ABI, and then plus 312.5J. All right. So if we separate out our I and our J, we have 2400 minus 10 alpha BD minus 600 equals 8 alpha AB. And then if we take our J components, we have what? 24 alpha AB. I'm sorry, not AB, BD. Sorry about that. 24 B alpha BD. And then that's minus 250 equals 312.5. So we can see that we'll solve that directly, plug that in, and get that. All right. So that's kind of the end once you've gotten to that point. So we solve, and actually won't even need another piece of paper. We can just write alpha BD is equal to 23.44. 23.4, that's in radians per second squared. And alpha AB turns out to be 195.7 radians per second squared. And since they're both positive, they're both counterclockwise. Okay. So that's that. That's a acceleration problem. Doesn't get much tougher than that, but it might get tougher with geometry. But again, it's the same idea regardless. You're going to go through and you're going to effectively start with velocity, find those, and then if you have two ends, like on this, you're going to have to figure out what it is relative to this end, what relative to that end, and then equate them. So I would encourage you to go through this one and really understand it. It's going to help you a lot. There's always a problem like this on the final. So, and we will spend more time on it, but we have to move on too. So this is one of those things I'm going to say is, it's like if you're going to jump out of a airplane, then make sure you have a parachute. And so this is one of those problems where that's your parachute. Okay, so I think that's good for now. Thanks for listening, and I will see you guys in class soon. Thank you very much. Bye-bye.